As water flows through a turbine or other device, the kinetic energy of the flowing river, tidal fluctuations or waves is converted into electricity by the device. As mentioned in the above introduction, hydrokinetic devices require a minimum current and water depth. The minimum current required to operate a hydrokinetic device is typically 2 to 4 knots. Optimum currents are in the 5 to 7 knot range. Hydrokinetic devices are ideally installed in locations with relatively steady flow throughout the year, locations not prone to serious flood events, turbulence, or extended periods of low water level. Hydrokinetic technologies produce renewable electricity by harnessing the kinetic energy of a body of water, the energy that results from its motion. Since water is 832 times denser than air, our tides, waves, ocean currents, and free-flowing rivers represent an untapped, powerful, highly concentrated, and clean energy source.
Basically, hydrokinetic energy is produced by harnessing the kinetic energy of a body of water. Since water is 832 times denser than air, our water, our tides, our waves, ocean currents, and free-flowing rivers represent an untapped and clean energy source. One of the processes is an oscillating water column. Waves enter and exit a partially submerged collector from below, causing the water column inside the collector to rise and fall. The changing water level acts like a piston as it drives air that is trapped in the device above the water into a turbine, producing electricity with a coupled generator. The next one is a point observer, where it utilizes wave energy from all directions at a single point by using the vertical motion of waves to act as a pump that pressurizes seawater, which drives the turbine. This type of device has many possible configurations. One configuration called a horse pump point observer consists of a surface floating buoy anchored to a seafloor, with the turbine device as a part of a vertical connection. The wave-induced vertical motion of the buoy causes the connection to expand and contract, producing the necessary pumping action. Through the engineering to generate device wave resonance, energy capture, and electricity generation by point observers can be maximized. Thirdly is the attenuator, where these devices rotate another attenuator by rotational motion, where it is used to pressurize a hydraulic piston that then drives the fluid through a motor, which then turns the coupled generator. Then that produces electricity. Finally is the overtopping device, where this device causes a floating reservoir while the waves break over the walls of the device. This reservoir creates a head of water, which then creates a pressure that causes the hydro turbine to move. And while the hydro turbine moves, it causes electricity.
Because no commercial hydrokinetic power projects are currently licensed and operating in the United States, it is difficult to estimate the cost of hydrokinetic power production. A 2005 report by the Electric Power Research Institute estimated that some U.S. utility-scale wave power projects could produce electricity for about 10 cents per kilowatt hour once the technology has matured. The present state of technology makes hydrokinetics a long-term investment opportunity with potentially significant but highly uncertain returns. In the meantime, the early stage of the technology and the high regulatory cost associated with lengthy permitting requirements and licensing uncertainties are likely to continue, presenting major economic hurdles to commercialization of the technology.
Currently, a lot of hydrokinetic and generation technologies are moving from demonstrational purposes to commercial uses, for which they will need to apply for federal operating license in the near future. Areas for good wave energy potential would be the West Coast, Hawaii, and Alaska. And for tidal energy would be the Puget Sound, San Francisco, and a variety of East Coast areas. And for rivers, it's obviously going to be in Mississippi, Missouri, and Yukon because they're the biggest rivers in the U.S. And as of 2011, the federal Energy Regulatory Commission, or known as FERC, has issued 70 preliminary permits for hydrokinetic projects. On a global scale, over 25 countries have initiated hydrokinetic activities, but the thing is, most of them are in the early commercial stage, such as in Suwa in South Korea, where they already started a prototype for the hydrokinetic energy, and also in Gujarat, India, where they proposed a 50 megawatt tidal current project.
Hydrokinetic energy has certainly made tremendous progress in the past decade. Indeed, most people would acknowledge that it has grown from being a little more than a mascot to a full-fledged member of the energy generation team. And yet, despite the fact that people as reputable as the National Renewable Energy Laboratory have come out and said that hydrokinetic energy could provide 80% of our electricity by 2050, there are still plenty of those who remain convinced that hydrokinetic energy will continue to play a little more than a minor role in our energy future. According to the Energy Information Administration, this source of clean energy could very possibly produce as much as 23 gigawatts by 2025 and 100 gigawatts by the year 2050. And this just barely scratches the surface of its technically achievable potential. This latter figure represents roughly 10% of our present generation capacity, a sizable chunk, especially considering that unlike solar or wind, this power can be far more predictable and reliable.
The positive impact of hydrokinetic energy is tremendous, where, for example, we would avoid using fossil fuels, for which they conduct greenhouse gases and other air pollutions, and these greenhouse gases are not a good thing for the environment. It has also been estimated that 13,000 megawatts of hydrokinetic capacity would be developed by 2025. That means, at full potential, it could generate around 400 terawatts per year, which is 10% of US demand in 2007. Assuming that hydrokinetic energy displaces the generation from the current mix of US fossil fuel power, this could avoid 250 million metric tons of carbon dioxide, or 4% of total US carbon dioxide emissions in 2007. And even though this is a small percentage, we have to take into account that we are talking about the US, which is one of the biggest fossil fuel users in the world.
While actual impacts of large-scale operations have not been observed, a range of potential impacts can be projected. For example, wave energy installations can require large expanses of ocean space, which could compete with other uses such as fishing and shipping and cause damage to marine life and habitats. Some tidal energy technologies are located at the mouths of ecologically sensitive estuary systems, which could cause changes in hydrology and salinity that negatively impacts animal and plant life.
And that's all, folks.